Does humanity truly understand the cost of becoming a multi-planetary civilization? We have long been fed a diet of romanticized space exploration, cinematic visions of astronauts walking effortlessly across alien landscapes, safe within pristine habitats. This ideal suggests stepping onto another planet is merely a natural migration. However, when we strip away the cinematic grandeur and confront the unyielding laws of physics, a more ominous reality emerges. The cosmos is not a welcoming cradle. It is an environment of absolute hostility, governed by forces fundamentally incompatible with human biology. However, when we strip away the cinematic grandeur and confront the unyielding laws of physics, a far more ominous reality emerges from the darkness of deep space. The cosmos is not a welcoming cradle waiting to embrace our species. It is an environment of absolute hostility, governed by forces that are fundamentally incompatible with human biology. To comprehend the true scale of this cosmic challenge, we must anchor ourselves in the concrete reality of the present moment. We find ourselves in the middle of the year 2026. At this precise point in our history, the grand balance of human spaceflight is no longer concerned with theoretical equations or distant dreams of the next century. The telemetry data streaming back to our command stations right now forces us to confront a brutal physical reality on the surface of Mars, a world that refuses to compromise with our existence. The most immediate and terrifying threat is not the distance or the freezing temperatures, but the very air, or lack thereof, that blankets the planet. The Martian atmospheric pressure is less than 1% of what we experience on Earth. This is not just a statistical anomaly. It is a direct death sentence for any unprotected biological entity. At this extreme low pressure, we cross a critical threshold known in physics as the Armstrong limit. Without a highly pressurized artificial envelope, the boiling point of water drops below the normal temperature of the human body. Consequently, all biological liquids, including the very blood circulating through your veins, the moisture on your lungs, and the fluids in your eyes, would instantly and violently boil at room temperature. Your circulatory system would rupture, and your body would fail within a matter of seconds. Beyond the invisible trap of the low-pressure atmosphere, the crimson surface itself presents a visible nightmare in the form of global electrostatic dust storms. Unlike the gentle rain or wind storms of our home planet, these Martian tempests are planet-wide engines of destruction. The dust particles are incredibly fine, measuring only a few micrometers across, and they are sharp and jagged due to the lack of liquid water to smooth their edges over time. Driven by fierce winds, these particles rub against one another, generating massive amounts of static electricity. These storms can envelop the entire planet for months at a time, completely swallowing any incoming sunlight and plunging the surface into total darkness. For human explorers, this means any solar energy infrastructure is rendered utterly useless. Furthermore, this electrostatic dust carries a highly toxic chemical composition, saturated with perchlorates, that can destroy human thyroid function if inhaled. The microscopic grains penetrate the tiniest seals, clogging air filtration systems, degrading spacesuit joints, and scratching the delicate optical lenses of our most sophisticated mechanical structures. This brings us to a profound scientific tension that defines the current era of space theory. How can human beings hope to survive and establish a permanent presence on an alien world when every single natural element of that planet actively seeks to destroy life? How do we build a fortress of survival against a vacuum that boils our blood and toxic storms that choke our machines? The traditional approach of transporting every single brick, steel beam, and bag of concrete across tens of millions of kilometers of empty space is a mathematical and economic impossibility. The rockets required to carry such immense payloads would be too heavy to escape the gravitational pull of our own planet. The solution to this existential paradox requires an entirely new paradigm of engineering, a complete breaking of our technical intuition. The answer does not arrive from Earth. It is already waiting on Mars. It lies in the deployment of a massive automated 3D printer and the utilization of the dark, iron-rich soil resting directly beneath the astronauts' boots. By transforming the very ground that threatens to bury us into the raw material for our survival, we are learning to rewrite the rules of architecture in the cosmos. To understand how we shape our survival structure from the ashes of a dead planet, let us first look at the macroeconomic turning point that altered the entire map of human space exploration. To understand the immense undertaking of building a permanent outpost on an alien world, it is useful to step back and examine how complex human enterprises are organized. Historically, expeditionary forces always establish a preliminary base at a nearby harbor to refine their engineering tools before crossing an untamed ocean. This systematic progression from a secure testing ground to the distant wilderness is the foundation of successful logistical planning. In the modern era of cosmic exploration, this precise methodology has been translated into an authoritative administrative roadmap. This analytical paradigm is explored deeply in this new space documentary, which examines how the cold equations of stellar logistics dictate the distribution of state capital across the heavens. This long-term blueprint explains a profound structural reorganization that reshaped the entire celestial landscape in the early months of the year 2026. For several consecutive fiscal cycles, a significant portion of national cosmic capital was allocated to a highly complex, automated engineering initiative known as the Mars Sample Return Program. The primary objective of this mission was to send an intricate network of robotic collectors to retrieve small tubes of surface soil and atmospheric gases, caching them for a future return vehicle to carry back to scientific laboratories. However, as administrative planners conducted comprehensive audits, they encountered an undeniable strategic tension. The financial demands of retrieving a few hundred grams of unrefined geological matter were expanding exponentially, threatening to consume the resources required for actual human survival systems. Consequently, in the early months of the year 2026, a historic macroeconomic decision was formally verified to postpone and structurally halt the funding for the Mars Sample Return Program. This structural shift was not a retreat from the Crimson World, but a profound reallocation of material resources. Instead of exhausting billions of dollars on automated rock collection vehicles, the state apparatus redirected these massive financial rivers toward the immediate development of crude infrastructure, long-duration life support chambers, and robust architectural construction technologies designed to support living human beings. This fiscal redirection is governed by a grand operational architecture formally designated as the Moon to Mars strategy. The internal logic of this blueprint operates on the exact same principles as the coastal harbor analogy. Before sending a crewed mission across a transit corridor that requires a journey of several months, engineers must verify their life support architecture under real cosmic conditions. Therefore, the state program has transformed the Moon into a massive space laboratory. The lunar surface functions precisely as a training ground in front of the house, a local celestial backyard where human teams can test their automated infrastructure without leaving the immediate vicinity of their native world. If a mechanical failure occurs on the lunar surface, a telemetry signal reaches ground control in less than 2 seconds, and a return capsule can carry the crew back to safety within a few days. On the surface of Mars, however, a similar malfunction would mean absolute isolation and certain death. By utilizing the lunar environment, human research teams are currently conducting exhaustive field tests on advanced automated 3D printers. These immense industrial systems are being forced to operate in extreme vacuum environments and fluctuating thermal ranges, refining the exact mechanical steps required to layer planetary material into structural components. At the same time, heavy autonomous rovers are traversing the jagged landscape, validating their mechanical durability, battery thermal management systems, and computerized obstacle avoidance software. Specialized chemical processors are also being tested to extract raw compounds from the local soil, establishing the fundamental operational frameworks for resource utilization. Every single mechanical component is being thoroughly refined in this local harbor. Once these modular networks achieve absolute operational reliability, they will be packed into transport hulls and deployed across the deep cosmic void to establish the first permanent settlements on the bleak and unyielding crimson plains of this distant alien territory. This shift in budget transformed theoretical blueprints into a tangible, concrete project in the heart of Earth's desert, challenging the limits of human endurance. The structural reality of an extraterrestrial outpost begins with the physical properties of the envelope that isolates human life from a deadly external environment. To understand how such an envelope transitions from an abstract design matrix into a functional shelter, analytical teams look directly at the physical anatomy of the primary testing installation known as Mars Dune Alpha. This containment structure covers a total geographical area of exactly 160 square meters. The structural footprint is deliberately optimized to maximize usable interior volume while minimizing the linear paths that a mechanical extrusion system must travel during construction. This entire habitat model was fabricated through automated additive manufacturing, utilizing a specialized industrial concrete matrix designed to simulate the exact silicate composition of Martian red sand. The automated machinery layered this synthetic regolith matrix to build an interlocking structural shell capable of distributing localized atmospheric loads evenly. Looking at this material assembly, determining rules of physics dictate the thickness of the outer barrier, turning simple geological sand into an impenetrable bunker. Moving past the outer shell of this simulated fortress allows us to observe the operational mechanics that govern the interior environment. A structural shield is meaningless without an active biological presence to test its internal systems under persistent stress. This critical dynamic is the core focus of the second Crew Health and Performance Exploration Analog mission, which represents a crucial milestone in modern space optimization frameworks. This specific phase of long-duration simulation is featured prominently in this new space documentary, which, bearing the inner layers of cosmic engineering, showcases how human architecture functions when separated from global logistics networks. As we trace the historical timeline into the middle of the year 2026, the 4-person astronaut crew of this second mission has officially surpassed the monumental milestone of over 200 days of absolute isolation. They are no longer living in a passive structure. They are living inside a highly dynamic, independent planetary engine that must self-regulate every single breath, calorie, and liter of moisture without relying on any external supply chain replenishment. The true nature of this physical confinement reveals itself through the cold, procedural friction of daily operations. The crew does not experience isolation as a simple, abstract concept, but as a series of rigid operational boundaries that challenge human instinct. For instance, whenever a crew member transmits a vital systems report or a personal message to the outside support network, they face a mandatory 20-minute communication signal delay. This temporal barrier means that a simple question and its subsequent answer require at least 40 minutes to complete, completely removing the possibility of real-time human conversation and forcing the team to develop absolute operational independence. When a critical climate control valve or an oxygen filtration unit experiences mechanical wear, there is no repair technician available to intervene. The inhabitants must perform all tasks of diagnosing, machining, and executing self-repairing operations for their equipment using a limited set of modular tools stored within the utility bay. Furthermore, their nutritional cycle is directly tied to their structural habitat. The crew maintains a specialized indoor agricultural pod, consuming self-grown food, such as fresh microgreens and specialized crops, harvested from automated hydroponic trays. This agricultural integration turns the living quarters into a literal biological feedback loop, where the physical health of the humans is explicitly dependent on the botanical health of the closed ecosystem they tend. As the months pass inside these printed walls, the physical constraints slowly reshape the cognitive landscape of the inhabitants. This long-duration empirical mission is scheduled to open its hatch and release the team at the end of October 2026, marking a full year of continuous operational tracking. The psychological data gathered across these hundreds of days provides planetary architects with an invaluable baseline for future deep space deployments. At this stage of our analytical journey, it is necessary to conduct a brief, periodic recap of the structural layers we have explored so far. we can see that the monumental task of building a planetary fortress is no longer merely a theoretical computer-aided engineering problem. Through the physical deployment of these actual printed models, human research organizations have conclusively proven that long-duration habitats are both biologically and psychologically feasible under strict isolation protocols. The physical envelope can support the human body, and the human mind can adapt to the crushing silence of an independent world. This structural success marks the successful validation of our initial architectural frameworks, proving that automated machinery can turn localized sand into an active shelter. This strategic understanding sets the necessary stage for examining deep planetary material interactions extensively. However, a conventional printed framework will quickly collapse under the ravages of space weather if we do not thoroughly understand the chemical nature of the native soil. To appreciate how a lifeless world can hide the foundation of future human architecture, it is necessary to transition our gaze from large macrostructures down to the microscopic, atomic reality embedded within alien stone. In our everyday experience on Earth, we understand that soil is not merely a collection of crushed rocks, but a dynamic geological ledger that records the history of the water, atmosphere, and organic matter that have interacted with it over vast stretches of deep time. When fine grains of sediment settle at the bottom of a quiet lake, they form dense sheets of clay. This clay behaves exactly like a prehistoric natural safe, sealing away microscopic particles between its tightly packed sheets and protecting them from external erosion. For billions of years, these layers compress, slowly transforming into solid stone while preserving an uncorrupted chemical diary within their subterranean vaults. Understanding this preservation mechanism allows us to build a precise intuition for why space agencies do not simply look at any random patch of desert, but instead target very specific ancient lakebeds where the invisible architectural building blocks of the universe might still remain intact. This specific search for subterranean secrets brings us directly to the wheels of a car-sized mechanical explorer wandering deep within the ancient boundaries of Gale Crater. For over a decade, NASA's Curiosity rover has crawled across this vast sedimentary basin, tracing the historical paths of ancient water flows. As explored in this immersive space documentary, decoding the raw chemistry of these extraterrestrial sandstones is a vital prerequisite for any future multiplanetary construction project, as it reveals the baseline stability of the materials humans will eventually use to build their homes. The rover eventually entered an area known to be Glen Torridon, a region rich in specialized clay minerals that attracted intense scientific scrutiny. Upon arriving at a specific geological formation designated as the Knockfarrell Hill member, the rover's robotic arm deployed its powerful drill, boring into the stone to collect fine, powdery fines from a bedrock layer that was deposited roughly 3.5 billion years ago. These powdered minerals were then carefully transferred into the internal laboratory of the machine, specifically inside the complex sample analysis at Mars Instrument Suite, setting the stage for a first-of-its-kind chemical experiment on another world. To analyze this ancient powder without destroying the delicate clues trapped inside, the automated laboratory performed a groundbreaking wet chemistry experiment, utilizing a highly specialized liquid reagent known as tetramethylammonium hydroxide. The introduction of this liquid reagent acts precisely like chemical scissors, breaking dense macromolecular structures into soluble fragments and tagging them so they can vaporize cleanly at lower temperatures inside the heated ovens. Inside the heated ovens of the instrument suite, the liquid solvent soaked into the 3.5 billion-year-old Martian clay, unbinding the fragile carbon architectures from the mineral matrices that had held them captive for eons. As the temperature rose steadily inside the chamber, these freed components transitioned into gases, allowing the onboard sensors to capture and map their precise atomic signatures for the very first time in human history. The telemetry data transmitted back across the empty space void revealed a stunning chemical tapestry hidden within the Knockfarrell Hill sandstone. The automated analysis confirmed the definitive presence of more than 20 distinct macromolecular organic carbon compounds, Rather than finding simple single carbon links, the instruments detected sophisticated cyclic and aromatic ring structures, including complex configurations like naphthalene and benzothiophene. Most importantly, these complex chains revealed a diverse mixture of compounds saturated with nitrogen and sulfur, elements that are universally recognized as the essential chemical building blocks required to spur complex material evolution. The discovery of these nitrogen heterocycles is a profound milestone, as these specific ringed architectures resemble the identical raw materials upon which the genetic structures of life are organized on our native world, proving that ancient Mars possessed a highly sophisticated and varied chemical inventory. The broader impact of this discovery forces a complete reevaluation of our future relationship with the red planet, validating a profound, thought-provoking statement. Martian soil and sand perfectly preserve primitive organic building blocks, despite billions of years of cosmic radiation bombardment. For decades, prevailing theories suggested that this environment was a thoroughly sterilized wasteland, entirely scrubbed of complex carbon chemistry by relentless solar winds. Curiosity's experiment shatters this assumption, proving that the local mudstone protection shields these complex structures over deep geologic time. Consequently, this planetary regolith transitions from an aggressive, toxic nuisance into an invaluable source of raw minerals for shaping building materials. Human construction teams can now plan to extract these stable carbon networks, processing them to create highly resilient defensive enclosures directly on the local surface grid. Once the chemical treasure trove in the ancient Earth's interior is deciphered, space engineers will officially activate the robotic arm of the 3D printer to begin a revolution in resource utilization. You sit at a terminal console located 40 minutes away by radio signal round trip. Your monitors show a cold, high-resolution graphic overlay of a desolate valley. You are an engineering controller overseeing the execution of a monumental construction cycle on an entirely different world. Every command you verify must pass through the vast emptiness of the interplanetary void before a multi-ton mechanical apparatus executes it on the surface. From this operational perspective, the sheer absurdity of standard logistics becomes instantly clear. Ferrying heavy terrestrial building materials across space remains an economic impossibility, as the staggering cost of escaping the deep gravitational well of our homeworld requires millions of dollars for every single kilogram of payload lifted into orbit. Attempting to ferry entire building materials across tens of millions of kilometers would cause the collapse of any national space budget before the first foundation could even be laid. This logistical barrier forces a radical shift to In Situ Resource Utilization, the absolute rule of living entirely off the land. To execute this operational shift, you activate a decentralized swarm of autonomous robotic excavators on your terminal screen. These mechanical vehicles crawl across the dark surface sand, utilizing robust scooping arms to gather the ubiquitous dark soil and readily available silicate minerals scattered across the ancient sedimentary basin. This raw planetary debris cannot simply be piled up. It must undergo an advanced mechanical transformation. The onboard artificial intelligence arrays inside each excavator continuously analyze the particle size distribution of the gathered regolith, ensuring that only the most stable mineral matrices enter the refinement stream. This real-time filtering process prevents structural microfractures from forming later within the printed layers. The gathered materials are routed into a centralized processing hopper attached to the primary construction vehicle. Here, the dry silicates are crushed and blended with a specialized liquid chemical binder, an organic polymer matrix specifically engineered to perform flawlessly under extreme sub-zero temperatures and vacuum conditions. This specific formulation ensures that the mixture does not crystallize prematurely during the high-pressure deposition cycle. This dynamic blending process forms an advanced silicate space mortar, a highly viscous extrusion ink. Laboratory evaluations demonstrate that once this indigenous mixture cures, it exhibits a compressive and tensile strength that far exceeds conventional terrestrial concrete, transforming fragile cosmic dust into an ultra-dense geological shield. This complex processing loop is detailed extensively within this new space documentary, which, bearing the inner layers of advanced celestial manufacturing, showcases how humanity bypasses traditional engineering constraints to secure a permanent foothold among the stars. Your computerized telemetry matrix now initiates the actual fabrication sequence. The automated printing system, suspended on a massive gantry structure, begins to move linearly along a pre-programmed architectural path. The heavy extrusion nozzle sprays the dense silicate mortar layer by layer, meticulously adhering to complex, mathematically verified self-supporting arch diagrams. Sensors mounted directly on the printhead constantly measure the localized atmospheric temperature and cure rates, dynamically adjusting the extrusion velocity to ensure flawless molecular cross-linking between each individual layer. Rather than utilizing flat, vulnerable ceilings that would instantly collapse under intense interior atmospheric tension, the system shapes sweeping parabolic vaults and interlocking geometric domes. These complex architectural forms distribute internal pressure stresses equally into the solid foundation grid. The automated printers continuously cycle, stacking consecutive rows of mortar until the protective walls reach a thickness of several meters. This massive thickness serves two existential purposes. Internally, these heavy geological hulls function as an unyielding physical restraint, containing the artificial atmospheric pressure required to keep human blood from boiling. Externally, the ultra-dense silicate walls completely absorb the relentless bombardment of solar winds and high-energy cosmic radiation that perpetually sterilizes the open desert. Reviewing the operational layers we have analyzed across these development cycles, we can synthesize a profound periodic summary. The toxic, iron-rich Martian mud, which originally presented an aggressive chemical threat to both human lungs and machine seals, has been systematically transformed through the sophisticated application of in situ resource utilization technology and automated 3D printing into the ultimate protective material. This engineered stone now stands as an absolute defensive shield, successfully isolating human biological life from the destructive chaos of high-energy charged particles. This material victory redefines our relationship with the Crimson Frontier, proving that our engineering intuition can conquer a dead world. By completely eliminating the old dependencies on planetary resupply from Earth, we establish a scalable manufacturing paradigm that can expand indefinitely across the alien planes, securing long-term human survival on this world. However, a sturdy, meter-thick rock wall framework will quickly turn into a dark tomb if we don't design tightly integrated functional zones inside it. To understand how a permanent outpost on the Crimson Planet functions as an integrated machine, one must analyze its internal spatial architecture. A thick, protective external shield of printed planetary sand is merely an inert shell without a systematic internal blueprint. Inside the heavy parabolic arches of the habitat, the living and working areas are precisely arranged according to a strict functional diagram. This compartmentalization ensures that distinct mechanical, biological, and physiological operations can coexist without interfering with one another. Each department operates as an independent node, directly connected to a centralized cosmic life cycle bus, maximizing efficiency while providing critical safety redundancies. By examining this internal configuration layer by layer, we can thoroughly understand how human civilization intends to systematically organize its daily operations far away from its native world. This systematic division of cosmic infrastructure represents a major focus within this comprehensive space documentary, providing an analytical breakdown of how industrial engineering secures human life within a hazardous extraterrestrial environment. Zone 1 represents the primary energy generation sector, which houses the mini-nuclear power grid. While early exploration blueprints favored solar panels due to weight constraints, actual telemetry has exposed major operational vulnerabilities in relying exclusively on sunlight. The Crimson Planet is frequently ravaged by massive electrostatic dust storms that can grow to encompass the entire globe, often lasting for several consecutive months. These dense, airborne tempests block almost all incoming solar radiation, plunging the planes into total darkness and completely paralyzing conventional photovoltaic cells. Without a constant supply of electricity, the habitat's life support systems would freeze, turning the facility into an unyielding tomb within days. To eliminate this existential risk, NASA has strategically integrated small, mobile nuclear fission reactors directly into the core architectural base blueprint. These robust power blocks operate entirely independently of atmospheric conditions, utilizing the heat from slow atomic decay to produce a steady, uninterrupted flow of electrical energy. This constant power stream keeps air pumps humming, thermal heaters warming, and computers calculating, even when the external atmosphere is completely choked by millions of tons of churning electrostatic dust. The second primary department clearly indicated on our master structural plan is the Psychological Preservation Core, which contains the soundproof private cabin zone. While heavy external industrial equipment and automated life support machinery are vital for physical long-term survival, the internal emotional stability of the explorers represents a highly delicate bottleneck that requires equal engineering attention. Living inside a confined space with a small group of individuals for hundreds of days, separated from the open skies and natural biomes of our home planet, can cause severe psychological strain. The persistent background rumble of support pumps, combined with the total lack of personal space, often induces severe sensory overload, deep depression, and intercrew friction. To mitigate these psychological hazards, architects have designed highly isolated, acoustically decoupled living cells. Each individual crew member has immediate access to a dedicated personal cabin lined with dense, sound-absorbing composite materials. Inside these quiet sanctuaries, the ambient noise of the base is reduced to absolute silence. This acoustic isolation allows the inhabitants to step out of their demanding professional roles, communicate privately with distant family networks on Earth, regulate their circadian rhythms under specialized light arrays, and recharge their cognitive faculties before returning to active operational duties. The final functional department, situated within our architectural loop, is the Resource Reclamation Infrastructure, centered on the Geological and Groundwater Extraction Command Station. Human survival on an arid alien world requires an unyielding local supply of raw, vital fluids, as transporting liquid weight across space remains economically impossible. This automated facility serves as the nervous system for an expansive network of deep subsurface drilling rovers deployed around the perimeter. The station constantly tracks and directs automated vehicles as they traverse the jagged terrain, utilizing specialized ground-penetrating radar to pinpoint vast, buried glaciers known as ice lenses. Once an underground ice pocket is officially verified, the command center coordinates heavy robotic drills to bore through meters of rocky regolith to reach the frozen deposits underneath. The extracted planetary ice is melted and routed directly back to the reclamation center through deeply insulated pipelines. Inside this facility, the water undergoes a multi-stage filtration cycle to eliminate out toxic compounds like perchlorates, successfully transforming raw extraterrestrial ice into pristine, life-sustaining drinking water. Furthermore, a substantial portion of this retrieved liquid is routed into specialized chemical separation chambers, where the molecules are broken apart and recombined to synthesize pure liquid oxygen and liquid hydrogen. This highly specialized domestic chemical factory provides the vital propellants required to refuel returning missiles, ensuring that the exploratory crew possesses a definitive path to safely escape the planetary gravity well whenever the mission cycle draws to a close. The mechanical interplay between atomic energy and this structural component is fundamental to the operation of a closed biological system where life is continuously regenerated from its own waste products. To truly comprehend the seamless operation of an extraterrestrial sanctuary, we must track the invisible, life-sustaining streams that circulate continuously through its mechanical veins. Let us trace the path of a single breath exhaled by a crew member resting inside the living quarters. The warm air, saturated with carbon dioxide, is drawn silently into an overhead intake vent by a low-frequency ventilation array. This carbon dioxide is not discarded into the freezing exterior vacuum. Instead, it is channeled through an intricate network of aluminum conduits embedded within the thick walls. This dark, stale airstream flows steadily toward a specialized agricultural hub, passing through automated environmental gates that carefully regulate pressure and humidity. As the air enters this brilliantly illuminated sanctuary, it encounters the artificial biological green lungs of the fortress. Here, thousands of genetically optimized crops are arranged in vertical hydroponic trays, bathed in a perpetual pink glow from specialized light-emitting diodes. The foliage of these plants immediately absorbs the carbon dioxide from human breath through microscopic pores on their leaves, executing a flawless biochemical conversion powered by artificial light. This continuous botanical processing unbinds the carbon atoms to fuel plant growth while releasing a torrent of fresh, pure oxygen back into the atmosphere. This crisp, filtered oxygen is immediately captured by ceiling collectors, sanitized through high-efficiency particulate air filters, and pumped back into the crew quarters, completing a perfect respiratory loop that sustains human biology without any external planetary air. As this airborne cycle refreshes the atmosphere, a parallel fluid journey unfolds beneath the floor plates, managing the most precious liquid asset in this arid wilderness. Let us follow the wastewater generated by the daily activities of the inhabitants, including gray water from personal hygiene stations, condensation collected from air conditioning units, and metabolic moisture from urine reclamation ports. This chemical mixture drains directly into an advanced multi-stage resource circulation system located in the lower engineering basement. The fluid is treated by heavy filtration units and pushed under mechanical pressure through dense, semi-permeable membranes to strip away compounds at an atomic level. The water then passes through ultraviolet disinfection chambers, where intense radiation sterilizes any remaining microorganisms. This deep purification process operates flawlessly hour after hour, turning what was once considered unusable secondary byproduct into pristine, highly refreshing, life-sustaining drinking fluid. This absolute wastewater treatment cycle effectively blurs the line between decomposition and life, transforming toxic waste back into an uncorrupted fluid resource. The purified output flows through insulated stainless steel tubes into the main reservoir, completely crystal clear and perfectly balanced with vital minerals, ready to be consumed again by the crew or routed into the automated crop watering lines. This intricate choreography of air and water does not function in isolation. It is entirely sustained by a continuous, independent thermal and electrical anchor. The immense energy required to drive the high-pressure filtration pumps, power the intense agricultural illumination banks, and maintain a stable internal climate is generated continuously by the silent decay of heavy atomic elements within the mobile nuclear reactor block. This nuclear core acts as the true heart of the habitat, circulating superheated coolant through independent heat exchangers to warm the facility against the extreme -80-degree chill of the outside hoar frost. By linking this nuclear power engine directly with the botanical filtration zones, engineers have successfully created a self-sufficient mechanical entity that operates independently of the volatile weather patterns plaguing the surrounding desert plains. The closed ecosystem mimics the deep planetary recycling loops of our native world on a miniature, highly controlled industrial scale, ensuring that every atom of carbon, oxygen, and hydrogen is endlessly repurposed to safely preserve human presence here. Standing inside the brightly lit and warm 3D-printed fortress amidst the bleak darkness of the Red Planet, humanity truly learns a profound lesson about its new place in the universe. The final assessment of our journey to the Red Planet brings us to a profound realization regarding the position of humanity within the cosmic hierarchy. For generations, our species has operated under the comforting illusion that we could conquer any frontier through sheer technological arrogance, carrying our familiar terrestrial comforts and manufactured building materials across the deep void. Yet, the stark physical reality of extraterrestrial colonization teaches us a harsh lesson in humility before the immutable laws of science. Our future home on Mars will not be built with the arrogance of materials brought from Earth. Instead, If we are to endure, our long-term presence must be meticulously molded from the toxic, iron-rich ashes of a dead world. We must humble our engineering desires to match the raw chemistry of the planetary regolith, acknowledging that survival requires adaptation to the harsh parameters of our host environment rather than a stubborn attempt to dominate it. From this perspective, those thick silicate structures layered by automated machines transition from mere engineering achievements into a profound testament of human endurance. These multi-meter walls are not an absolute guarantee of cosmic safety. They represent just a tiny brushstroke on the vast, expanding map of humanity's knowledge against the unrelenting ravages of interplanetary space. The milestones verified by NASA throughout the year 2026 stand as an unyielding proof of our species' unwavering will. By transforming a sterilized radioactive desert into a highly controlled, self-sustaining cradle of survival, this structural project officially opens the historic gateway for humanity to cross the threshold into a true multi-planetary era. We are no longer passive observers bounded by a single atmospheric envelope. We are actively writing the opening chapter of our permanent cosmic displacement. The unyielding silence of the Red Plains reminds us that this journey is merely the beginning of a much grander odyssey across the starless void. The universe remains vast, and our current understanding is simply an incomplete ledger waiting for the next generation of researchers to fill its pages. What do you think? Does the reality of rebuilding our entire civilization from alien sand alter how you perceive our future among the stars? Take a brief moment to leave your profound analytical thoughts in the comments section below, as every unique perspective drives our collective human quest for deep cosmic understanding across this endless black starry expanse.